At this very moment, the sun could vanish, and we would have no idea. For 8 full minutes, Earth would continue orbiting empty space, bathed in sunlight that no longer has a source. The sky would look normal. Birds would still be flying, traffic would still be moving. Every clock on Earth would tick forward, unaware that its star is already gone. Then the light would switch off, not dim, not fade, off. And when it does, something even more unsettling follows. Gravity disappears too, because the sun is not just our light. It is the mass that anchors the entire solar system. Remove it, and Earth does not stay in orbit. It flies forward into interstellar darkness at 30 kilometers per second. This is not mythology, it is physics. The question is not whether we would survive. The question is how long we would even understand what happened. There is a particular kind of stillness that comes before any system fails. Before the bridge collapses, it holds. Before the power grid goes dark, it hums. Before the diagnosis arrives, the body feels entirely ordinary. The failure is already happening, but the evidence hasn't reached you yet. The sun disappearing would be the most extreme version of that lag between reality and awareness that any living creature could ever face. And understanding why requires starting not with catastrophe, but with something far more fundamental: the nature of light itself, and what it means for information to travel. Light moves at approximately 300,000 kilometers per second. That number is so large it resists intuition. In 1 second, a photon of light can travel the equivalent of 7.5 times around the entire circumference of the Earth. It can cross the distance from the Earth to the Moon in about 1.3 seconds. These are not abstract facts. They are the operating rules of the universe, hard constraints that apply not just to light, but to every signal, every force, every piece of information that can pass between 2 points in space. The sun sits about 150 million kilometers from Earth. That sounds like a large number, and it is. But on cosmic scales, it is extraordinarily close. Our nearest stellar neighbor, Proxima Centauri, sits more than 40 trillion kilometers away. The Sun, by comparison, is practically at arm's length. And yet, even across that intimate distance, light still requires roughly 8 minutes and 20 seconds to make the crossing. This is not a communication delay in any technological sense. It cannot be upgraded, rerouted, or compressed. It is a fundamental feature of space-time. Whatever happens at the sun, we learn about it just over 8 minutes later, and not a moment sooner. This has been true for every sunrise in Earth's history, and it would remain true even at the moment the sun ceased to exist. So picture the scenario with full physical honesty. The sun vanishes, not by exploding, not by dimming, not by any process we would recognize as natural, but simply by ceasing to be present. The photons it emitted 8.3 minutes ago are already in transit. They are already crossing the void between the sun and Earth, carrying the last image of a star that no longer exists. They will arrive. They will illuminate our sky. They will heat our atmosphere and cast shadows and trigger photosynthesis, all while their source sits somewhere in the galaxy as a blank region of empty space. For those 8.3 minutes, the fraud is total. There is no way to detect it. Every instrument humans have built to observe the sun operates by receiving something the sun sends outward: light, radiation, particles. In the absence of the sun, those instruments would simply receive nothing new. But the old signal, the last one, is already traveling. It fills our sky normally. It tells every solar panel and thermometer and photovoltaic satellite that everything is fine. Then it ends. The moment the last photons arrive is not a gradual event. This is worth dwelling on, because the human brain instinctively models large-scale change as gradual. We expect sunsets to dim before they go dark, fires to gutter before they die. But the sun's disappearance would produce no sunset analog. One moment, the sun would be in the sky. The next moment, that region of sky would be as dark as any other region of the sky at night. The transition would occur at the speed of light, which from our perspective means it would be instantaneous. This is daytime on Earth, in whatever hemisphere currently faces the sun. The sun simply vanishes. No flash, no warning glow. The light source is gone, and the sky begins doing what the sky does when there is no sun. It goes dark, not gradually, as in a normal sunset, but immediately, as the last photons pass and no new ones follow. The day side of Earth plunges into a darkness unlike any it has experienced in human memory. Not the darkness of night, which is softened by moonlight and starlight, and the slow adjustment of eyes. Not the darkness of a solar eclipse, which lasts minutes and announces itself with the geometry of shadow. This darkness arrives mid-sentence. It arrives while children are at school and farmers are in their fields and pilots are navigating bright skies. It is absolute in the sense that the primary light source for the entire inner solar system has simply ceased contributing. The night side of Earth notices nothing unusual at first. People sleeping through what they believe is ordinary night would not yet know anything had changed. The moon, which reflects sunlight, would also eventually go dark. But again, not instantly. The moon is about 1.3 light seconds away from the point in space where the sun had been. The last reflected sunlight would vanish from the moon just over a second after the last direct sunlight reached Earth. For those on the night side watching the moon, it would blink out. Not dim, blink. And then there is the question of what comes next, which is almost entirely a question of survival timescales. Not for human civilization in the abstract, but for the physical environment in concrete, measurable terms. The surface of the Earth loses its primary energy source immediately, not in any political or logistical sense. The infrastructure, the fossil fuels, the nuclear power plants, the stored energy in batteries and reservoirs, all of that remains entirely unaffected. What changes is the continuous incoming solar energy that has maintained the climate system for billions of years. That flow stops the moment the last photon arrives. Earth's atmosphere is extraordinarily efficient at retaining heat in the short term. This is the same property that drives climate change. The greenhouse effect, in which certain gases trap outgoing infrared radiation and slow the loss of heat to space. In the days immediately following the sun's disappearance, the same mechanism would work in humanity's favor. The lower atmosphere would cool, but slowly. Average global temperatures would drop by only a few degrees within the first week. Cold, but survivable. Uncomfortable, but not immediately lethal. The first week would be a period of profound psychological and logistical crisis, but not yet a physical extinction event. Power grids would remain operational wherever they were powered by nuclear, geothermal, or pre-stored sources. Food supplies would be unaffected in the short term. The oceans, which hold an enormous thermal mass, would cool extraordinarily slowly. They are essentially vast batteries of stored solar energy, and their warmth would buffer coastal climates for months. But the atmosphere above that thermal buffer is a different story. As days turn to weeks, the upper atmosphere would cool dramatically faster than the lower levels. The tropopause, the boundary between the troposphere and the stratosphere, would shift. Weather systems driven by temperature differentials and solar heating would begin behaving unusually. The jet streams, which depend on latitudinal temperature contrasts, ultimately traced back to differential solar heating, would weaken and become erratic. Not because they disappear immediately, but because the gradients sustaining them are no longer being renewed. Within weeks, temperatures in the mid-latitudes would drop tens of degrees below their former averages. Snow would fall at latitudes where it normally never appears. Tropical regions, buffered initially by oceanic warmth, would still be relatively mild by comparison. But the cold would be advancing from the poles with a pace driven not by seasons, but by the sheer and absolute cessation of incoming energy. A useful frame for imagining this is to look at what happens during volcanic winters. Events like the 1816 Year Without a Summer, following the eruption of Mount Tambora. That event reduced global temperatures by less than a single degree Celsius. It caused crop failures across Europe and North America, contributed to famine in parts of Asia, and remains one of the most disruptive single years in modern history. The sun's disappearance would be categorically different in scale. Not a fraction of a degree, not a temporary aerosol veil, but a permanent and total cessation of the energy source that all surface life depends upon. The plant layer of Earth's biosphere would begin dying within days, certainly within weeks. Photosynthesis requires light. Without it, plants cannot produce sugars, cannot maintain their cellular machinery, cannot grow. Trees with their stored energy reserves would survive longer than grasses. Some seeds and dormant organisms deep in soil would survive for years. But the living green layer of the planet, the forests, the crops, the phytoplankton blooming at the ocean surface, would begin collapsing with the first lost growing season. And the food webs depending on it would collapse in sequence behind. This is the structure of an extinction event. Not a single dramatic blow, but a cascade of failing dependencies, each one removing the foundation from the layer above it. Among the details of human survival in such a scenario, one fact stands out as genuinely surprising. Geothermal heat. The Earth's interior is hot, not because of the sun. The sun heats only the surface. The Earth's interior is hot because of the residual thermal energy from the planet's formation 4.5 billion years ago, and because of the ongoing radioactive decay of elements like uranium, thorium, and potassium distributed throughout the mantle and crust. This is entirely independent of solar energy. It would continue regardless of whether the sun existed. The average geothermal gradient, The rate at which temperature increases as you descend into the crust is roughly 25 to 30 degrees Celsius per kilometer in most regions, though it varies significantly. This means that at a depth of 1 kilometer, temperatures are already above the surface ambient temperature by 25 to 30 degrees, even in the coldest climates. At 2 kilometers, they are warmer still. At depths of several kilometers, temperatures are high enough to boil water. This is not an efficient heating system for a civilization accustomed to sunlight, but it is a real energy source, and it points toward a theoretical survival corridor that physicists and science communicators have explored seriously. The average temperature of the deep ocean floor is approximately 2 to 4 degrees Celsius, maintained in part by geothermal venting. The deepest parts of the ocean, far from surface cooling, would maintain liquid water for far longer than the surface would. Hydrothermal vent ecosystems, which have never depended on sunlight at all, might continue functioning indefinitely. This distinction matters because it clarifies what kind of catastrophe the sun's disappearance actually is. By convection in the liquid iron outer, by convection in the liquid iron outer core would persist. Plate tectonics might eventually slow as the mantle gradually cooled over geological timescales, but that process would take hundreds of millions of years. What dies in the scenario of the sun's disappearance is the surface biosphere, not the planet, not its deep geology, not even all of its microbial life, but the surface layer, the thin skin of warmth and light and liquid water that allowed complexity to arise. That dies. Now the scenario takes a turn that is often omitted from popular discussions, and it is the most physically disorienting part of the entire thought experiment. Gravity vanishes too. This requires explanation because gravity does not feel like something that could simply stop. It feels foundational. It is the reason we stand on the ground, the reason the atmosphere stays attached to the planet, the reason the moon does not drift away. Gravity, in everyday experience, is the bedrock of physical reality. The idea of it disappearing is almost impossible to model intuitively. But gravity obeys the same speed limit as light. This follows from Einstein's general relativity, which describes gravity not as an instantaneous force acting between masses, as Newton's original formulation approximated, but as a distortion in space-time caused by mass and energy. That distortion propagates. Changes in a gravitational field travel outward at the speed of light. When the sun's mass disappears, the distortion it created in the space-time around it begins to relax, and that relaxation propagates outward at 300,000 kilometers per second. The practical consequence is identical to the situation with light. For 8.3 minutes after the sun disappears, Earth's orbit continues normally. Earth curves around the empty point in space where the sun had been, because the gravitational field has not yet updated. The space-time distortion created by the sun's former mass is still present. It has not yet received the information that the mass is gone. And so, Earth follows the path that distortion dictates, continuing its elliptical trajectory around nothing. At 8 minutes and 20 seconds, the leading edge of the gravity wave, if we can call it that, arrives at Earth. At this same moment, the last photons of sunlight too also arrive. The sky goes dark, and the gravitational anchor point disappears simultaneously. Not sequentially, not within moments of each other, but at precisely the same instant, because both signals travel at the same speed from the same source distance. And then Earth is no longer in orbit. A body in orbit is always moving. Earth travels at approximately 29.8 kilometers per second around the Sun. It is in continuous free fall, always falling toward the Sun, but moving laterally fast enough that it perpetually misses. That is what orbit means. Remove the center of gravitational attraction, and the free fall component disappears. What remains is pure lateral motion. Earth's inertia carries it forward in the direction it was moving. At the moment gravity vanished, in a straight line, at its full orbital velocity of nearly 30 kilometers per second. This is not slow. In a single day, Earth would travel approximately 2.6 million kilometers from its former orbital position. In a year, it would travel almost 940 million kilometers, roughly the distance from the Sun to Jupiter. The planet would not break apart. It would not explode. It would simply fly forward into the interstellar medium, taking its moon with it, gradually cooling, gradually darkening, carrying everything that had ever lived on its surface as a frozen geological record into the depths of the galaxy. Saturn's rings would not immediately vanish. The outer planets would continue orbiting the phantom gravitational field for minutes after the Sun disappeared. Longer for the more distant ones, because the gravity wave takes longer to reach them. Neptune, the outermost planet, orbits at about 4.5 billion kilometers from the Sun. The gravity wave, traveling at the speed of light, would take 4 hours to reach Neptune. For 4 hours after the Sun's disappearance, Neptune would continue its slow, faithful orbit around empty space. Its 165-year trip around the Sun, which it has been making for the entire history of the solar system, would continue for 4 more hours after the star was already gone. This cascading wave of gravitational notification, Earth notified at 8 minutes, Jupiter at 43 minutes, Saturn at 79 minutes, Uranus at 159 minutes, Neptune at 249 minutes, is one of the most striking features of the scenario. It reveals something about the nature of physical reality that is easy to miss in everyday life. No information about any event is instantaneous. Every part of the solar system lives in its own temporal bubble, separated from every other part by the time it takes light to cross the distance between them. We tend to imagine the solar system as a synchronized whole. All its parts move in concert, all of them aware of each other's existence simultaneously. But that is an illusion produced by the smallness of the time delays relative to human timescales. The Moon knew about the September 11th attacks 1.3 seconds after they happened. Mars knew about them anywhere from 3 to 22 minutes later, depending on its position in its orbit. The information travels, and it is never instantaneous, even within what we consider our immediate cosmic neighborhood. The Sun's disappearance would simply make that fact impossible to ignore. There is a question embedded in this scenario that rarely gets examined directly. Why would the Sun disappear? The answer, from a physics standpoint, is that it almost certainly could not. Not like this. Not through any natural mechanism currently known to science. Stars do not vanish. They evolve, they expand, they exhaust their nuclear fuel, they collapse or explode or fade. But they do not simply cease to exist from one moment to the next. The sudden removal of the sun's mass and energy with no precursor and no remaining trace would violate conservation of energy, which is one of the most robust principles in all of physics. As far as we know, it cannot happen. This is important not because it makes the scenario irrelevant. Thought experiments do not require physical plausibility, but because acknowledging it changes the intellectual texture of what we are exploring. This is not a scenario about a specific danger that Earth faces. The sun will eventually die, but that death is approximately 5 billion years away, and it will be extraordinarily slow by human standards. The sun gradually brightening, expanding into a red giant, eventually shedding its outer layers and leaving behind a white dwarf. There will be warnings spanning millions of years. The thought experiment is interesting because it isolates the sun's functions one by one and asks, what exactly does it do for us? And how quickly would we feel the absence of each function? We have touched on light and gravity, but there is a third function that receives almost no attention in popular treatments of this scenario, and it is arguably the most profound. The sun as a long-term driver of geological and biological stability. Life on Earth did not arise because the Earth happened to be warm. Life arose because the Earth is warm in a very specific and sustained way, within a very specific range, maintained over billions of years with remarkable consistency. The sun is the primary reason for that consistency. But the sun is not just a passive radiator. Its ultraviolet radiation shapes the chemistry of the upper atmosphere. Its radiation pressure contributes to the structure of the magnetosphere. Its gravitational pull stabilizes the inner solar system's orbital dynamics, reducing the probability of catastrophic asteroid impacts on geological timescales. None of these effects would vanish immediately upon the sun's disappearance, but they illuminate the degree to which the sun is not just a feature of Earth's environment. It is the organizing principle of the entire inner solar system's stability. Life, as we understand it, did not merely require warmth, it required reliable warmth, consistent enough across hundreds of millions of years to allow chemistry to become biology, biology to become complexity, complexity to become consciousness. The sun provided that reliability, not perfectly. There were mass extinctions, ice ages, volcanic winters, and at least one episode, approximately 700 million years ago, when the entire Earth may have been covered in ice. But even through those disruptions, the sun kept shining. The base energy input was always there, always slightly adjustable by changes in orbital mechanics or atmospheric chemistry, but always present. Remove it, and the biological clock that has been running for 3.5 billion years simply stops. Not gracefully, not with a transition period that allows adaptation. It stops the way a mechanical watch stops when its mainspring breaks. All at once, mid-motion, leaving the hands frozen at whatever position they held when the mechanism failed. Within a year of the sun's disappearance, the surface of the Earth would be roughly at the temperature of liquid nitrogen, somewhere around -100 to negative 150 degrees Celsius, depending on location. This estimate comes from comparing Earth's energy budget with the expected rate of heat loss to space. The atmosphere would begin collapsing. Nitrogen and oxygen, which make up nearly all of the atmosphere, would remain gaseous down to about negative 196 degrees Celsius for nitrogen and negative 183 degrees for oxygen. So the atmosphere would persist for some time, but the water vapor content would drop dramatically as water froze everywhere on the surface, and the carbon dioxide in the atmosphere would eventually freeze as well, precipitating out as dry ice around negative 78 degrees Celsius. This is where the picture becomes simultaneously more dire and more precise. A world without solar energy is not just cold. It is systematically losing the chemical and thermal complexity that life depends on. The biochemical reactions that sustain even the most cold-tolerant organisms require liquid water. Below 0 degrees Celsius at standard pressure, liquid water does not exist. Life as we know it, all of it, from bacteria to blue whales, requires liquid water to remain metabolically active. Certain organisms can survive freezing. Tardigrades, for instance, can enter a state called cryptobiosis, in which their metabolism virtually stops and remain viable for years in frozen conditions. Some bacteria can survive in frozen rock at temperatures as low as negative 20 degrees Celsius. These are extraordinary adaptations, but they are survival states, not living states. The organisms are not reproducing, not metabolizing, not doing the things that define life as an active process. They are waiting for warmth that will not come. Unless, as we noted, you go deep enough. The hydrothermal vent communities of the deep ocean, clustered around the mid-ocean ridges where tectonic plates pull apart and magma comes close to the ocean floor, do not depend on sunlight. They depend on chemosynthesis, in which bacteria use chemical energy from hydrogen sulfide and other compounds venting from the ocean floor to produce organic matter. The entire food web at these vents, tube worms, shrimp, crabs, fish, ultimately traces its energy not to the sun, but to Earth's interior heat. These communities would survive. In the increasingly cold, increasingly dark ocean, they would be isolated oases of warmth and chemistry in an otherwise freezing world. Whether any complex multicellular life could make a sustained living at these vents without the rest of the ocean's food web supporting them is uncertain. But the principle is clear. The deepest, geothermally supported life on Earth would outlast everything on the surface by an enormous margin. By 1,000 years after the sun's disappearance, the surface of the Earth would be unrecognizable. The ocean's surface would be frozen solid to a depth of several kilometers. The atmosphere, depleted of water vapor and losing carbon dioxide to the surface as dry ice, would be thinner and colder. The polar regions would be first to experience the most extreme conditions. The equatorial regions, modestly buffered by residual oceanic heat, might remain slightly less catastrophic for longer. The planet would continue its journey through the galaxy, moving at 30 kilometers per second. After 1,000 years, it would have traveled approximately 950 billion kilometers, well outside the solar system's former position, somewhere in the interstellar medium between stars. The night sky, viewed from this frozen world, if any observer could somehow exist to witness it, would look different than it does today. The constellations would appear similar, but shifted. The stars would still be visible, their ancient light arriving from across the galaxy, carrying their usual information about nuclear reactions happening in distant suns. And among those stars, somewhere in the direction of the galactic center, there would be one place in the sky where a star was missing that had been there before. A gap in the familiar pattern, an absence that, to any observer who knew where to look and what to look for, would mark the location of something that had once been home. This is the moment where the physics of the scenario begins to touch something harder to quantify than temperature gradients or orbital mechanics. Human civilization has spent the entirety of its existence oriented toward the sun. Not merely in the logistical sense, not merely in the sense that sunlight powers agriculture and sets the rhythm of the day, but in a deeper orientation of meaning and identity. The sun has been the central reference point of human cosmology across essentially every culture that has ever existed, not always as a god, but always as something foundational, the thing that rises and sets, the thing that tells you where you are and what time it is, the measure against which everything else is arranged. There is a reason, the Copernican revolution, the demonstration that the Earth orbits the sun rather than the sun orbiting the Earth, was experienced not just as a scientific correction, but as a profound disruption of the human sense of place. The question of whether the sun or the Earth is at the center of the solar system turned out, psychologically, to be a question about whether humans were at the center of something meaningful. Copernicus said we were not at the center. It took a century and a half, and the work of Galileo, Kepler, and Newton to fully absorb the implications. The sun's disappearance would be the end point of a much longer journey of displacement. First, the Earth was moved from the center of the cosmos. Then the sun itself was revealed to be one star among hundreds of billions in a galaxy that is itself one among hundreds of billions of galaxies. The sun is not special by cosmic standards. It is a G-type main sequence star, middle-aged, middle-sized, unremarkable in every astrophysical sense. There are stars in the galaxy older than the sun will ever be. There are stars larger than the sun's entire orbit around the galactic center. There are planetary systems orbiting stars far more stable and long-lived than our own. And yet the sun is the one that made us. That is not a trivial fact. The vast majority of the universe's mass and energy has absolutely nothing to do with the existence of life on Earth. But this one star, this particular fusion reactor, 1.4 million kilometers in diameter, located in this particular arm of this particular galaxy, is causally responsible for every form of life that has ever existed on this planet. Every evolutionary line, every ecosystem, every organism, every thought that any conscious creature has ever had, traces its energy backward through food chains and geological time to the same single photon-producing source. That asymmetry between cosmic insignificance and biological necessity is one of the genuinely strange features of our situation. There is a detail in the physics of this scenario that has been touched on but deserves a fuller examination. The 8-minute lag. It is tempting to think of those 8 minutes primarily as a survival reprieve, the last sunlight warming the last day before darkness. But the 8-minute lag is also a statement about epistemology, about the relationship between observation and reality. When you look at the sun, not directly, obviously, but in any measurement of its light, you are not seeing the sun as it is. You're seeing the sun as it was 8.3 minutes ago. This is always true. The sun you observe is always a historical document, not a live feed. Most of the time, this distinction is purely academic. The sun does not change significantly over 8.3 minutes, and the difference between the sun now and the sun 8 minutes ago is negligible for any practical purpose. But what if that lag is not academic? What if something did happen to the sun in the last 8 minutes, and you simply have not received the information yet? This question extends outward into the entire observable universe. Everything we observe in the night sky is a historical record. The moon as it was 1.3 seconds ago. The nearest stars as they were years ago. The Andromeda Galaxy as it was 2.5 million years ago. The cosmic microwave background radiation as it was approximately 380,000 years after the Big Bang. Almost 13.8 billion years ago. The universe we observe is not the universe that exists. It is the universe that existed, reconstructed from light and radiation that took various amounts of time to reach us. The further we look backward in time. The most distant objects we can detect, quasars at the edge of the observable universe, are being seen as they were when the universe was less than 1 billion years old. Some of them almost certainly no longer exist in the form we observe. They may have merged with other galaxies, collapsed, or changed beyond recognition in the billions of years since their light began its journey toward us. We are surrounded by ghosts, not in any metaphysical sense, but in a precise physical one. The light from a dead star arrives for thousands of years after the star has ceased to exist. From our perspective, the star is still there, still shining, still burning, still participating in our observation of the sky. We cannot know it is gone until the last photon from its final moment reaches us. And depending on how far away it was, that delay could be thousands of years, or millions. The sun is close enough that we would know within 8 minutes. Most stars are far enough that we would never know in any human lifetime. There is a class of astronomical events in which this delay has direct relevance. Gamma-ray bursts, the most energetic explosions in the observable universe, are believed to occur when massive stars collapse or when neutron stars merge. They release more energy in seconds than the sun will release in its entire 10 billion year lifetime. And they are directional. They emit their energy in narrow jets. If a gamma-ray burst occurred in our galaxy, pointed toward Earth, and was close enough, it could strip away a significant portion of Earth's ozone layer, exposing the surface to lethal levels of ultraviolet radiation. We would have no warning. The burst travels at the speed of light. Any signal we could receive would arrive with the burst itself. The light from the explosion and the gamma radiation would arrive simultaneously because they both travel at the same speed. There would be no early warning system, no evacuation, no preparation. There would simply be the ordinary guy, and then the event. This is not a variant of the sun disappearance scenario in its details, but it shares the same fundamental structure. A catastrophic change in our stellar environment, arriving at the speed of light with no advance notice possible because no information can travel faster than the signal itself. The universe, in this sense, is structurally indifferent to the survival requirements of conscious beings. It does not provide early warning systems. It does not account for the time it takes awareness to catch up with events. The lag between what happens and what we can know is not a flaw in our instruments. It is a basic feature of the physics that governs all information transmission. Something worth pausing on is the question of what an advanced civilization might be able to do differently. This is not a discussion about science fiction technologies. It is a more modest question. Is there any plausible physical mechanism by which a civilization with far greater technological capability than our own could receive advance warning of a stellar event? Gravitational waves might offer a partial answer. Gravitational waves are ripples in space-time produced by the acceleration of massive objects. Particularly dramatic events like the merger of black holes or neutron stars. They were detected for the first time in 2015 by the LIGO observatories, a scientific achievement that opened an entirely new way of observing the universe. Unlike light, gravitational waves interact very weakly with matter, which means they pass through essentially everything without being absorbed or scattered. They carry information about events in the universe that cannot be extracted from electromagnetic observation alone. But gravitational waves also travel at the speed of light. They do not offer a faster-than-light information channel. An event that happens 150 million kilometers away will send gravitational waves that arrive at Earth at the same time as the light from the event. There is no shortcut. Neutrinos are another candidate. When massive stars collapse into supernovae, they release an enormous burst of neutrinos. Far more energy in neutrinos than in visible light, in fact. And those neutrinos emerge from the collapsing core slightly before the optical explosion. When supernova 1987A exploded in the Large Magellanic Cloud, neutrino detectors on Earth registered the burst roughly 3 hours before the visible light from the explosion arrived. This offered a small, genuine advance warning. But the sun is not going to supernova. It is too small. And in the hypothetical scenario of instant disappearance, there would be no collapsing core, no neutrino burst, no precursor signal of any kind. The sun would simply be absent, and all information about its absence, whether carried by light, gravity waves, or neutrinos, would travel at the same speed and arrive at the same time. If you follow the logic of this scenario through to its endpoint, you arrive at a picture that is simultaneously sobering and clarifying. The life of the solar system as we know it depends on a single star. That star could, in principle, be disrupted. Not by vanishing. That is physically implausible. But by changes in its output, by changes in our orbit, by changes in the interstellar environment. Any of these would change conditions on Earth. Some combinations of changes could make the surface uninhabitable. The history of Earth's climate contains evidence of multiple near extinctions driven by changes in solar energy input, atmospheric chemistry, and orbital mechanics. We exist in what is called the Goldilocks zone, the range of orbital distances from a star within which liquid water can exist on a planet's surface, given the right atmospheric conditions. But the Goldilocks zone is not a fixed physical region. It changes as the star evolves. The Sun is currently brightening by about 10% every billion years. The inner boundary of the Sun's habitable zone is gradually moving outward. In approximately 1 to 2 billion years, depending on geological and atmospheric feedback processes, Earth may cross the inner boundary. The surface temperature rising enough to trigger a runaway greenhouse effect that would boil the oceans and render the planet permanently uninhabitable. This is the Sun's actual long-term danger to life on Earth. Not disappearance. The opposite. Too much brightness. Too much warmth. The same energy source that made life possible gradually becoming incompatible with the conditions life requires. On a human timescale, this is irrelevant. A billion years is 200 times longer than the history of all complex animal life on Earth. It is incomprehensibly far ahead. But it illustrates the essential fragility of the relationship between a planet and its star. The window in which life is possible on a planetary surface is not permanent. It is not guaranteed. It is a consequence of specific physical conditions that happen to be aligned correctly right now, in this particular moment of cosmic history. We are, in a very literal sense, the product of a coincidence. Not a mysterious coincidence, not a planned one, but a physical one. The coincidence that the Sun is the right size, the right age, and the right distance from Earth to allow liquid water and complex chemistry to persist for long enough to produce everything we are. The thought experiment of the Sun's disappearance has a way of making that coincidence visible that ordinary contemplation of the solar system does not. When everything is working, it is easy to treat the Sun as furniture, a feature of the environment so constant and so reliable that it barely registers as something that could be otherwise. The thought experiment removes it, and in removing it, reveals the architecture of dependency beneath. Every photon of sunlight that has ever reached Earth has been doing work, driving weather, powering photosynthesis, evaporating water into the atmosphere, maintaining the temperature range that keeps the oceans liquid, slowly bleaching rocks on mountaintops through UV exposure, driving the chemical cycles that regulate the composition of the atmosphere. The Sun does not merely light the sky. It runs a system, an interlocked, interdependent, extraordinarily complex system of energy flows that sustains every living thing. The 8-minute lag before we would know the Sun had gone is the signature of that system's architecture. The physics that makes the lag possible, the finite speed of light, the speed of light propagation of gravity, the fundamental constraint on how fast information can travel, is the same physics that allowed the solar system to form, that keeps the planets in stable orbits, that governs every nuclear reaction in the Sun's core. It is not an accident or an oversight. It is a consequence of the same deep structure of the universe that allowed us to come into being at all. There is something honest about sitting with this, not catastrophizing it, not finding existential horror in it, but just acknowledging the precision of the conditions that made us possible and the degree to which we inhabit a window of viability rather than a permanent home. If the sun disappeared right now, this moment, the first indication any human being would have would be the same for everyone on the day side of the planet. The sky going dark, not metaphorically, literally. The photons end and darkness replaces them. From the night side, it would be subtler. The moon going dark a second later, the planets, Venus, Mars, Jupiter, visible in the pre-dawn sky, eventually winking out as the gravity wave reached them and they drifted out of the orbital positions where reflected sunlight would have reached Earth. One by one, over the course of hours, the familiar lights of the solar system would leave the sky until only the stars remained, only the light from other suns, some of it millions of years old, crossing incomprehensible distances to arrive in a sky that had just lost its own. In the silence and the cold that would follow, the universe would continue exactly as it had been. The same 300 billion stars in the Milky Way burning, the same 2 trillion galaxies distributed across the observable universe, the same cosmic microwave background, the faint afterglow of the Big Bang, filling space in every direction, the same dark matter, the same dark energy, the same expansion of space carrying galaxies apart from one another at ever-increasing rates. The universe would not notice. The universe has never noticed us. That is not a tragic fact. It is simply an accurate one. What would remain, at least for a while, would be the physical reality of everything that had ever happened here. The geological layers, the fossil record, the frozen remnants of cities and forests and oceans. A planet carrying, in its crust and its ice, 3.5 billion years of biological experiments. Every branching and extinction and adaptation and innovation, compressed into stone and sediment and ice. A record of what life can do, given a star and a rocky planet and 4 billion years. Earth would carry that record outward into the galaxy. Not as a message because there is no one to receive it, but as a fact, as a thing that happened in a universe 13.8 billion years old, in a galaxy containing hundreds of billions of stars, on a planet orbiting one of the quieter ones. Something extraordinary occurred. Matter organized itself into structures capable of wondering where the light came from and what would happen if it went away. The fact that we can ask the question is, in its own way, the most remarkable thing about the scenario. More remarkable than the 8-minute delay. More remarkable than the frozen atmosphere or the untethered orbit or the dying biosphere. We can ask what happens when the sun disappears, and in asking, we reveal that we understand, at least partially, what the sun is. We understand nuclear fusion. We understand orbital mechanics. We understand the speed of light and general relativity and the thermodynamics of planetary cooling. We understand, with real precision, how the system works. That understanding is itself a product of sunlight. Every generation of scientists who contributed to it lived and worked and thought under this same star. Their knowledge is, in a lineage stretching back to the first photosynthetic organisms, sunlight in a different form. Organized, compressed, made abstract and transmissible, but traceable in its origins to the same fusion reactions 150 million kilometers away. When we describe what would happen if the sun disappeared, we are using the sun's own light, converted through billions of years of biological and cultural evolution, to understand itself. The star is thinking about its own absence through us. That is a strange loop. It is not mystical, it is physical, but it is strange enough to be worth noticing. The sun will not disappear. It will brighten, expand, and eventually, in approximately 5 billion years, exhale its outer layers into space as a planetary nebula, leaving behind a cooling white dwarf about the size of the Earth but containing most of its original mass. That white dwarf will cool for trillions of years, eventually becoming a hypothetical black dwarf, a cold, dark remnant that emits no light, essentially invisible against the background of deep space. By that point, the universe will be approximately 100 times older than it is now. The night sky as we know it will be unrecognizable as stars burn out and are not replaced. The stellar era of the universe, the era we currently inhabit, in which ordinary stars shine and planets orbit them, and chemistry is possible, will be giving way to a darker, colder era. In that context, the current moment is not ordinary. It is, cosmically speaking, a peak. Conditions for life in the universe are, by some estimates, better now than they have ever been before in cosmic history, and they will gradually worsen from here on geological and astronomical timescales. We are not arriving at the party late. We are, in a meaningful sense, at one of the high points. The light is on. For now, and for a very long time to come, the light is on. Understanding what it would mean to lose it, really understanding it, in the physical detail that the thought experiment demands, is perhaps the most direct way of appreciating what it means to have it. 8 minutes. That is the distance between the sun and the understanding of its absence. In those 8 minutes, contained in a sphere of outward traveling light, is the last image of a star that has made every living thing on Earth possible. If it were to go, we would spend those 8 minutes in the warmth of light that no longer had a source, watching birds and traffic and the ordinary passage of the day. And in that ordinariness, in the gap between what is real and what we can know, is a quiet summary of the human condition itself. We live always some number of minutes behind the facts. We act on information that is already history by the time it reaches us. We inhabit a present that is constructed from the recent past. The sun's 8-minute lag is just the clearest version of a principle that runs through all of physical reality. Nothing is instantaneous. Everything arrives with a delay. The universe updates on a schedule we do not control, and we build our understanding of it from signals that left their sources some time ago. We are, all of us, living in the light of a star we cannot see in real time. We are trusting that it is still there because the light is still arriving. So far, it always has been.